Who we got here today? The four of us? Five of us. Always, JR, always. All right. We are currently live. Let's see if anyone joins us today. Did you watch us yesterday, Elise? You didn't participate in the live chat. You left that to Talia and Nathan to do. Okay. While we're waiting for people to join us, did anyone keep going with the problem set 6 questions and want to talk about any of them? Anyone have any specific questions that they want to go through? We've got a couple of people watching us now. Please write something when you join us so that I know who is with us. Who's with us? Please write something in the chat when you join so that I know who you are. Okay, do we want to go over anything from problem set 6? Who did questions at home on problem set 6? Who does the problem set at home that I tell you to? We should be able to do 5, 6, and 7 now. Have we been working through them? Okay, we've got Paranitha, we've got Talia, and one more mystery person who hasn't written anything yet. Quick survey. Who does the problem sets? Yeah? Have you finished any of them? But you've been working through them? Also working through them? Working through them? Working through them. Cool. Paranitha and Talia, feel free to join in the conversation and let me know whether you're doing the problem sets or not. We should now have enough information to be able to do problem sets 5, 6, and 7 from the book. 5, 6, and 7. Thanks, Paranitha and Talia. Keep working through them. Like I've said before, if we get to the end of a topic and you have done every single question from all the problem sets in the book, then that's wonderful. There's not much better you can do. Also, like the other questions and stuff that I give you, of course. But this is the place to start. Do all the questions, and that is setting you up perfectly. So we should have enough information now to do problem sets 5, 6, and 7. Yeah, we should have 5, 6, and 7. Okay, what we're talking about today is we're just going to spend a few minutes going through some of the applications of all the stuff that we've been talking about. Where are radioactive materials actually used in everyday things? I'm just going to run and grab my whiteboard markers. I'll be back in a second. All right. Okay, sorry, we don't need it. Okay, there are 3 main uses of radioactive materials that we're going to go through today. 3 main ones that you need to know about, and then obviously the stuff that we've spoken about already, like if you remember a couple of weeks ago, we spoke about using radiation in like a factory as quality control. Do you remember speaking about that? With the juice question, yeah, exactly, Prachi, yeah. So those kind of things, we need to be able to apply our knowledge to those as well. But in terms of like classic applications of radioactive materials, there are 3 main ones we're going to go through today. So I'm going to write all 3 of them up on the board. The first one is called traces. The second one is for dating. And the third one is smoke detectors. The topic is applications of radioactivity. Paranitha and Talia, can you guys see the words on the board at all? Or anyone else that's watching that's joined us now? Okay, Talia says yes. Excellent. Okay, so 3 main applications. Applications of radiation, of radioactivity. That's the topic for today. I'll write that up. So that, yeah, I know it's kind of blurry. I'm going to try and do my best. Let me know if there's any like specific word that doesn't make sense, but I'll read out everything that I put up on the board. So hopefully if you can't see it exactly, you'll be able to write it down because I'll call it all out. So the topic is applications of radioactivity. Let's call it of radioisotopes. Applications of radioisotopes. Okay, 3 classic applications: tracers, dating, and smoke detectors. The first one, tracers. I'm just going to chat to you guys for a minute about what that means. I'll show you a quick video that demonstrates it really well. And then before I show you that video, I want you to try and apply your knowledge of the different types of radiation to tell me, and I'm going to do that for the first one and the third one, for you to tell me which type of radiation we would use for this. So a tracer can be used in a lot of different things. We can use tracers in humans for medical purposes. We can use tracers to track where certain waste products end up. And the point is this: if we want to be able to trace, we want to be able to track something, to know the path that something takes, we're going to put some radioactive material into that thing. How will that allow us to track where it goes? Okay, so what will spread out? The radiation, good. Radiation will spread out from the source, exactly. Radiation will spread out from the source. What instrument would I use to find where the radiation is coming from? A Geiger tube, good. A Geiger tube or a Geiger counter. So I could point my Geiger counter around and find the place where the radiation is coming from, right? Because that'll be the place where that has the highest activity, right? Yeah, exactly, Nathan. Geiger counter. Yes, so we can follow the radiation to the source using the Geiger tube or the Geiger counter, and we can find where it is. So, for example, for medical purposes, we might get a person to swallow a radioactive source, and then we could track that through the body. Or we could put a radioactive source into a factory that produces waste. We put a radioactive source in there, that means we can follow where the waste ends up. We can follow the path that waste takes if we want to know where it's all going to go. So we might want to use it for waste. We might want to use it for medical purposes. And the point is, we put the radioactive source in the person or in the material, and we can follow where the radiation is coming from as the source moves down the track, which means we can track where the thing is going, where the whole thing is going. Knowing what you know about radioactive sources, which type of radiation would I want to use if I was using a radioactive source as a tracer? Hey, what's up? Is the door locked? Yeah, sure. You got a class in there. What type of radioactive source would I want to use? Nathan says, what do we know about radioactive sources? Well, last week, you guys remember, we filled in that whole table. We know about what are the main things that determine like the properties of the radioactive source. There were the last couple of columns. Specifically, we're looking at ionizing power, good, and penetrating power, exactly. We want to know how good it is at ionizing and how good it is at penetrating. Okay, so if we're using a radioactive source as a tracer, do we want it to be good or bad at penetrating? Good. Why? Exactly. If you're swallowing a radioactive source, we need to be able to measure the radiation from that source from outside the body, which means we need to be able to penetrate to the outside. Good. So we want it to be pretty good at penetrating. Exactly. Nathan says we might then want to use gamma radiation because that will because then the source won't be blocked by the things in the way and we'll be able to measure it. Good. What about ionizing power? Do we want it to be good at ionizing or bad at ionizing? Bad. Why, Babita? Exactly. We don't want it to damage us, right? So if we swallowed, which type of radiation is good at ionizing? Alpha, exactly. So if we swallowed a source, an alpha radiation source, that would be really bad for us. Yeah, exactly. Yeah, because exactly. So it's going to emit those alpha particles inside our body and probably ionize. Sorry? Will it hurt if you swallow an alpha particle? It depends how much radiation it's giving off. If it's a big alpha particle, if it's a big source, radiation source with a high activity, then it means you're going to be exposed to a lot of radiation. Now, remember, we can calculate how bad it's going to be for you. Yeah, do you remember the equation that we used to calculate the DE? What did DE stand for? Good. Dose equivalent. Good. And what was the dose equivalent equal to?
Absorbed dose multiplied by the quality factor.
Exactly. Absorbed dose multiplied by the quality factor. So, Chogal, to your question, if I knew how big the source was that I was swallowing, then I could estimate the absorbed dose, right? Now, the point is that if it's alpha radiation, then I'm going to be multiplying that by, what's the quality factor for alpha particles? 20, exactly. I'm going to be multiplying it by 20. So the dose equivalent is going to be pretty high. Just quickly, while we're on this, remind me, what do we measure absorbed dose in? What's the units? Grays. Good. Grays. And what do we measure dose equivalent in? Yeah, you're looking at the right word. You just got to remember how to say it. You're mispronouncing the V as a W. Maybe you wrote it down wrong. It's sieverts. Yeah, sieverts. Sieverts. Okay. Yes. Good job, Talia and Nathan. I like the fact that you guys are joining in and answering my questions on the live chat. Continue doing that, please. Okay, so the point of that is that if we swallowed an alpha particle, it wouldn't be very good for us because it's got a high quality factor because it's good at doing what? Ionizing, exactly. So we want traces, we want radioactive traces to be either gamma or they could also be beta as well. We could use either. All right. Let's watch a short video that's going to show us an example, a specific example of radioactive traces used in medicine. So I'm going to erase what's on the board. People at home, can you see the video?
Radioactive substances that emit thermals, like titanium, will be injected into the body to produce images.
Okay, if you can't see the video at home, I'll post a link to it on Connect, so you can watch it later.
15-year-old Daniel was born with a hole in the heart. He's been coming to Guy's Hospital in London since he was 2. Today, he's going for technetium injection. Radioactive technetium is pretty dangerous stuff, but a small measured amount of it can detect a life-threatening medical condition. For Daniel, radioactive imaging is the best way to make sure his heart is functioning correctly. But first, Daniel's technetium injection has to be made up in the hot lab. Safety clothes and radiation monitors have to be worn to protect the staff.
This is where the radioactive technetium is produced, and this is what we're going to use to make up Daniel's kit this afternoon. I'm going to use a syringe and needle to draw the radioactive technetium, but to protect myself from the gamma rays, I'm going to insert it inside a lead syringe shield. And at the front, you can see there is lead now, so that I can see through into the syringe what I'm actually drawing up. The radioactive kit is now ready to be taken out and used to inject Daniel.
The technetium is taken to the preparation room, where the exact dose is carefully measured. The dose is small enough to create a good image of Daniel's heart, without putting him at too much risk from the dangerous effects of radiation.
I now have my dose. I'll take it to the camera in this protected lead box. I'll just completely ready for the scan down there. And continue it down that way. I'm going to move the camera down to be very close to your cheeks. Right? You won't move once it's in the right position. Okay? In a minute, Penny's going to give you the injection and put a keep still for about 5 minutes. Okay? The camera's going to be detecting the gamma rays so that we can take pictures of your heart.
As the technetium is injected into Daniel's arm, we can see it being taken up by the bloodstream, which will finally make its way to his heart. Radioactive imaging has many advantages over X-rays. A standard X-ray only produces a static image, but radioactive images enable scientists to see body functions such as blood flow and even bone growth. Here we can see gamma images of 2 kidneys. They reveal that one kidney is actually larger than the other. There are other types of radioactive substances used in imaging, like radiofluorine. Again, a gamma camera is used to detect the gamma rays emitted by radiofluorine. Here we have an X-ray and a radioactive image of the same hand. On the left is the standard X-ray, but it was the radioactive image that detected the non-cancerous growth.
All right. That makes sense. What was going on there? So they injected the radioactive source into the bloodstream, and then because you could trace it, because it was giving off the radiation, you could trace it as it went through the bloodstream into the heart, and then as it was in the heart, it then filled it, so you could then take like an image of the heart, and you could do the same thing with different organs in the body as well. Is it a liquid? I can't remember which one they used in that video, so I'm not sure, but it would be something that it was a liquid. Cool. Yeah, liquid would make sense because then it could be properly taken up by the bloodstream. Hey, what's up, Jess? Through the S8 as well. Yeah, sure. Okay. Before we move on, quick side comment. Nathan has just posted saying, guys, I just realized the atom on the Star Wars book is a lithium atom because it's got 3 electrons and it's got 6 particles in the nucleus, which we assume would then be 3 protons and 3 neutrons. So very good, Nathan. It would be a lithium-3. A lithium-6 atom. Yes, very good. Although, as we spoke about, This is actually an incorrect drawing of an atom. Do you remember speaking about that before? How that's not actually what an atom looks like, but it's a good model. Okay, let's move on. So that is one application, radioactive traces used in medicine and other things as well. Another application is dating. By dating, I do not mean going on dates. I mean what we might call radiocarbon dating. Yes, Nathan, it is carbon dating. That is exactly what it is. Okay, get out your periodic tables, please. Radiocarbon dating makes use of an isotope, carbon-14, which is a radioisotope. Carbon-14 is a radioisotope. Let's draw the symbol for carbon-14. Elise, help me out. Good. The 6 on the bottom. Now, there is another common isotope of carbon. Anyone know, do you remember? We spoke about this a couple of weeks ago. What's the other main isotope? Not 16, no. 12, good. So carbon-12 is like the stable isotope of carbon. Carbon-14 is the radioisotope. It's radioactive. And when it decays, it turns into a nitrogen atom. What's the atomic number of nitrogen, please, Prachi? 7. So if that's all we knew at the moment, what type of radiation would that be? If carbon-14 is turning into nitrogen, which type of radiation is that? Beta negative, good. So what else is, what would be the number up here, first of all? 14 still, exactly. Because what happens in beta negative radiation? What's going on there? Say again? A new proton. Where does that new proton come from? Where does the new proton come from? Talia and Paranitha, good job. It's beta negative. See if you can tell me, where does the new proton come from in beta negative decay? Do we just like invent a new proton out of thin air? It comes from a neutron. Good. It comes from a neutron. A neutron in carbon-14 has turned into a proton. And what else has it turned into? A particle. What's its mass number? 0, because our mass numbers have to be conserved. Yeah. And what would its -1 would be its atomic number? Good. So what particle is that? What's the normal name we give to it? What's the normal name we give to it? An electron. It's an electron. It's got a relative mass of 0. It's not actually 0. It's just 2 times lighter than a proton or a neutron. So we say it's basically 0. And it's got a charge of -1. What else? There's one last thing produced in this. An anti-neutrino. Drawn like that. Cool. Okay, so this is the process of carbon-14 undergoing beta- decay. All right. Now, what we need to understand for radiocarbon dating is this. Where do we find carbon in nature? What types of things have carbon in them? Carbon dioxide, good. Coal, okay, coal. Where did coal come from? What did you say? Wood. Yeah. So what type of things have carbon? So carbon dioxide. What type of things take in carbon dioxide? Humans. What other things take in carbon dioxide? Plants. Anything that is living. Anything that is living has carbon in it. Not water. Water's not living. Water's H2O. Anything that is organic. Good use of the word organic there, Nathan. Anything living, anything that's organic has carbon in it. That's people, it's plants, it's anything that is or was alive has a lot of carbon in it. Okay? Now, the carbon that we have in us is a mixture of carbon-14 and carbon-12. So all organic matter has a combination of carbon-14 and carbon-12. Carbon-14 is radioactive. Carbon-12 is stable. But there is a set ratio of carbon-12 to carbon-14 in the atmosphere, because carbon-14 is being produced in the atmosphere at a constant rate. So as we live and we eat food that has carbon in it, and we breathe in and create carbon dioxide through cellular respiration and all those kind of things, we have in us a set ratio of carbon-12 to carbon-14. Okay? Is that clear? Every single human has the same ratio, carbon-12 to carbon-14. Can it be changed? Well, we assume no, it stays constant. While you're alive, you're constantly taking in carbon from the environment. And so the carbon that you're taking in, since that has a set ratio of carbon-12 to carbon-14, we assume that the ratio in your body of carbon-12 to carbon-14 stays constant. Okay? But what happens when a living thing dies? What starts to happen to all the carbon-14 in their body? It decays. Good, Prachi. It decays. Which means over time, after an organism has died, what will happen to the ratio of carbon-12 to carbon-14? It starts changing. What will there start being a greater proportion of? C12, exactly. The carbon-12 stays there because it doesn't decay. The carbon-14 decays. Now, the half-life of carbon-14, is approximately 5,370 years. Sorry, I've got that wrong. Those two numbers are swapped the wrong way around. It's 5,730. Okay, Nathan, I'm just going to correct something that you've said there. Nathan wrote, the longer an organism is dead, the more carbon-12 is present. It's not that there's more carbon-12 present. The amount of carbon-12 stays the same. It's just that there's what? What has changed? The amount of carbon-14. So it's not that the amount of carbon has changed. It's that the ratio of carbon-12 to 14 has changed. What's up, Alan? Yes, of course you may. All right. So that means that what scientists do is they take a fossil that they find. All right. So let's say you're on an archaeological dig and you discover a fossil of a human. How do they know? And then they say, like, this fossil is 30,000 years old. How do they know that? Exactly. They take a bit of that fossil and they test it to see how much carbon-12 is in it and how much carbon-14 is in it. They look at what ratio carbon-12 to carbon-14 is in that fossil, and they compare it to what? Exactly. The ratio of carbon-12 to carbon-14 in a living human. And they can then compare those ratios and say, we know the half-life, so that means we can estimate how long this organism has been dead for. Does that make sense? Now, it's not just with fossils that we can do that. If you're on an archaeological dig and you discover a wooden spear buried underground, a wooden spear, what would you do? Describe the process that the scientist would do. Sorry? Take a bit of the spear, good, and do what with it? Good. Good, they would take a piece of currently living wood, yes. Okay, so the exact maths is, we might do a practice question to use that exact maths, but what's more important is that you understand the process. Okay, so let's add one last bullet point to this. So that means that by comparing, so after an organism dies, the ratio of C12 to C14 increases, because there's now going to be the same amount of carbon-12 but less carbon-14. So the ratio of carbon-12 to carbon-14 will increase, and therefore we can compare, by comparing the ratio in the dead organism to the living one, we can estimate the time that the organism has been dead for. Okay, we've got a question from a couple of questions. Paranitha asks, what is the accepted ratio of carbon-12 to carbon-14? I'm actually not sure of that off the top of my head. I'm pretty sure it's different for different organisms. That's something that you can look up. I don't know exactly what it is. There's an accepted value in the environment. That might be what Paranitha is referring to. Again, I'm not sure what it is off the top of my head. We can look it up. Nathan says, would you want a sample of wood that's the same as the spear though? Right, yeah, exactly. So ideally you would want like the same type of wood, although you might be able to do extra calculations to work out even if you don't have the exact same type of wood. So for example, we can find fossils of dinosaurs and work out how long ago they died, even though we don't have currently living dinosaurs to compare it to. And that's because, as Paranitha is referring to there is a set ratio of carbon-12 to carbon-14 in the environment. So it might be that different organisms do slightly different things, but generally it's going to be the same for all organisms. It's going to be more or less the same for all organisms because we're all breathing in the same carbon. We're all living in the same environment, same atmosphere, which means we're all going to have roughly the same ratios in our bodies. And due to different things, specific organisms might have slightly different, but scientists can take that into account if it's the case. All right? Cool. There was one last one. Can I erase this, or are we still writing down? There was one last one I put up, and it was smoke detectors. Okay, this might seem like a pretty small thing. This is like one device, right? It's not like the whole industry of radiocarbon dating or of medical tracers or whatever. This is like one specific thing, but it's a good example of how radiation is actually used. And there's been a couple of questions I've seen in past exams where they've mentioned this I've seen it in the section 3 section of comprehension where they give you a thing about smoke detectors. So it's worth knowing about. Smoke detectors would work like this. You have a chamber. In that chamber is a radioactive source in a box. And separately, there is a radioactive, let's call it a Geiger counter. It's not necessarily a Geiger counter, it's just something that can measure radiation, but let's call it a Geiger counter. All right. Now, generally, on a normal day, this would be filled with normal air from the room, which means that the particles that this source is emitting will reach the Geiger counter, and so the counts will be high. You with me? So on a normal day, it's filled with air. If there's a fire in the room, what will this get filled with? Smoke. Exactly. It will get filled with smoke. Now, we want to build a device where when it gets filled with smoke, what's the difference between smoke and air? Which one is denser? Smoke. Well, yeah, that might be counterintuitive because they always tell you, like, if it's smoky, then you crawl, because that's because the smoke is hot, right? So it rises. But the smoke is heavier. It's made of heavier particles. It's hot. That's why it rises to the top. But the point is that if you're a little radioactive particle that's flying through air or through smoke, it's going to be harder for you to fly through smoke. You with me? So when it fills with smoke, what will happen to the reading on the Geiger counter? It will drop. So there'll be an electrical device wired into the smoke detector that if the reading on the Geiger counter drops below a certain amount, it triggers an alarm. Does that make sense? Now, this is for you to think. What type of radioactive source would I want in my smoke detector? It's going to be either alpha, beta, or gamma. Hands up for gamma. Hands up for beta. Hands up for alpha. Okay, Chogyal, why did you vote for beta? It's not harmful. Okay. Let's jump to beta. Why did you say alpha? Good. That's the key. Low penetration power. Beta particles, Chogyal, they're going to fly straight through that smoke. There's not going to be any difference whether it's air or smoke in there. They'll fly straight through no matter what. The point is it's going to be alpha because alpha has low penetration power. Good. Specifically, the general one used is a source that we've actually seen before, americium-241. That's the one we used in class, right? It's a source of alpha particles. Now, there are two things about americium-241. First of all, it emits alpha particles, which is what we want, so that it will get stopped by the smoke. You with me? The second thing is, would we want this to have a short half-life or a long half-life? 10 seconds to think. Do we want it to be a short or a long half-life? Think practically. Hands up for short half-life. Hands up for long half-life. All right, Elise, why'd you say short? Okay, more count so you can measure better. Good logic. Chogyal, why'd you say long? Yeah, long half-life. And what's the advantage to that? Why would we want less decay? So that what? Okay. Elise's logic, I think, was better than yours, but you're actually correct. So, Elise, it makes sense to say that we want a short half-life so that there's more counts. But what's a way we can fix that? How could we have more counts even if it's a shorter, even if it's a really long half-life? What would we do?
Source.
Exactly, Babita. We would just have more of it, right? We would just get a bigger source if we need more counts. The reason why we want a long half-life is for really practical purposes. What's the problem if you have a short half-life? It'll decay faster, and therefore, why is that just going to be annoying if you're a homeowner with a radioactive? You have to? Yeah, you have to change it really often. If it's got a short half-life of, a couple of days or a few minutes or whatever, then like every few months you're running low on americium-241 and you have to replace your sensor, your source, right? Whereas what we want is a source that has a half-life of maybe a few years, which americium-241 has, and therefore it'll be a few years until we have to replace it again. I don't know if those are the ones they use here in the school, but they are used. It's not just like a random demonstration for the purposes of science. They actually are used. Americium-241 smoke detectors, yeah, emitters of alpha particles. Okay. Yes, exactly. Paranithera and Talia, excellent input there. Okay. Before I hang up on the live stream, are there any questions on any of this from you guys or from the people watching from home? Sorry, I didn't like write up notes for this. It was more important for me to have a discussion so that we understand it. But feel free to write down some things from that discussion. Everyone at home, feel free to post some questions if you have them. Yes, Nathan, I'm going to explain to everyone what I want you to do in a second, but yeah, we're going to be continuing with problem set 6. Yes. Everyone at home, actually, don't hang up yet. There's something I want to go through with you all. Okay, this is kind of annoying because I can't find a blue one to put up for you. Here we go. There we go. That's what I want. Okay, sorry, Nathan, I know there's a lot of suspense, but what I'd like to do before you guys go is, I did this with the class that was here a couple of days ago. Before you continue with problem set 6, which is what I want you to do, can you all see the graph on the board? Let's have the lights up to make it easier. Okay, those of you that are here in class, you can follow along through with me anyway as we do this. At least were you here when we did this 2 days ago? Cool. Okay, so this is an example of a decay curve. I'm just going to run through this one more time, and you guys, because you know this already, can help me with it so that everyone at home can see what I want you to do. One of the things you need to be able to do with half-life, okay, Paranithera, it's okay if you can't see the numbers because I'll explain what they are, but can you see the curve and the shape of the graph? That's what's most important. That's the most important thing. I'll try angle this so that it's better for you. Okay. What we have here is down the y-axis, we have the activity. The counts per minute. What's that measured in? Becquerels. Good. And then along here, we have time measured in days. Okay. What's going to happen to the activity is that over time, as the sample undergoes decay, the activity is obviously going to drop as well. So what we need to be able to do is use a graph like this to calculate the half-life of the sample. So the way I want you to do this is exactly how I want you to show your work if you get a question like this in a test or exam. It starts up here. The number up here is 80. That's an 80 up there. So that means it's starting with an activity of 80 becquerels. That means the beta. After the first half-life, what will its activity be? 40 becquerels, exactly. 40 becquerels is down here. So what I'm going to do is then, I'm going to draw a line across from 40 becquerels until I hit the curve. What do I do with that then, Prachi? Exactly. I'm going to drop that down and see how long it took. So it took me 2 days. That's a number 2 over there. For those people at home that can't see the numbers, that's a number 2. It took me 2 days to get from 80 to 40. What would I do next, Elise? Exactly. I'm just going to do another 1 or 2 of these to see if it is the same every time. So half of 40 is 20. So I'm going to say when I drop down to 20 becquerels, how long did that take me? That took me 4 days in total, which means it's another 2 days. And then we might do 1 more. So the next one will be 10 exactly. When I halve it again, it'll be 10. And that takes me all the way to 6 days, which means the half-life for this sample is 2 days, exactly. Half-life would be equal to 2 days. So for those of you at home, I went through this with everyone a couple of days ago in class. That is how I want you to show your working for questions where it gets you to calculate the half-life given a curve. So in problem set 6, question 2 gets you to do that. So give that a go, please. We're going to continue working on problem set 6, and then for the rest of throughout the rest of the week, everyone should continue, please, working on problem sets 5, 6, and 7 at home. We're moving on to some pretty tricky things next week, leaving this stuff about half-life and nuclear decay and moving on to talk about nuclear fission and fusion. It's a slightly different topic, and it gets tricky with some new concepts that we're introducing. So I need you over the weekend to do some work on problem sets 5, 6, and 7 so that you've got all of that down before we move on to the next one. Okay. Paranitha, the red curve is showing you the activity as it changes over time. So the y-axis is the activity, and every half-life, that activity is going to halve. So that's what the red curve is showing you. Talia says, I drew a graph similar to that, but the x-axis was the half-life, and the y-axis was the percentage remaining from the Pearson textbook. Yeah, so it's possible that these numbers down here, Talia, instead of being the activity, it could be the number of particles left over or the percentage of particles left over. Because remember, we can swap between activity and number of particles, and the curve will look the same for both of them. So yes, Talia, it's the same concept. It would just be, instead of these numbers for the activity, it would start with 100% of the things left over. Then for that first line, you'd want to draw it at 50% left over. And then the next line at 25% left over, etc. Cool. I'm hanging up the live stream. Email me if you have any questions. Please continue working on problem sets 5, 6, and 7.